In this video, I'm going to do a paper reading of the small-scale proxies for large-scale transformer training instabilities paper. This is by Mitchell, Worstman, et al. From Google DeepMind. And as I've been doing in these paper reading videos, I also have Claude open, and I've provided the paper as context in the project knowledge for Claude. And I'm going to start out by asking Claude to summarize in one paragraph what this paper is about. So this paper examines training instabilities in large transformer models that can be reproduced in smaller models by using high learning rates. It focuses on two specific instabilities: attention logit growth and output logit divergence, showing that mitigations effective at large scale, the mitigations are qk-layernorm and z-loss regularization, also work for smaller models. The authors introduced learning rate sensitivity as a metric to show or to measure how robust models are across different learning rates, finding that sensitivity increases with model scale, especially when scaling depth rather than width. They demonstrate that training instabilities can be predicted before they occur by analyzing scaling trends of model characteristics like gradient and activation norms. Additional findings include that longer warm-up periods and independently scaling weight decay reduce learning rate sensitivity, and that gradient norms decrease with model scale and learning rate, potentially causing issues with default optimizer hyperparameters as models grow larger. Okay, so I had a feeling it was a very rich paper, and then this kind of confirms that. So it sounds like logit growth and output logit divergence. I'm not sure what output logit divergence means. I don't know what qk-layernorm and z-loss regularization mean. Let's see. Gradient and activation norms. I am familiar with those, and I think I've even calculated them with code, but I would need a refresher on that. Warm-up periods. I haven't like coded a scheduler, but I've been looking at cosine annealing schedulers, so that's familiar. Weight decay, I'm familiar. Gradient norms again, and yeah, so cool. Let's dig in. So what I've been trying to balance in these videos is kind of reading verbatim things that I need to read verbatim and then kind of just summarizing as I go. So yeah, we'll just go with the flow. So teams that have trained large transformer-based models have reported training instabilities at large scale that did not appear when training with the same hyperparameters at smaller scales. The causes are of interest. The amount of resources required to reproduce them have made investigation difficult. So they want to reproduce and study training stability and instability at smaller scales. The growth of logits in attention layers and the divergence of the output logits from the log probabilities. So highlighting this because I still don't really understand what that means. By measuring the relationship between learning rate and learning and loss across scales, we show that these instabilities also appear in small models when training at high learning rates and are equally effective for small models. Investigate other optimizer model interventions such as warm-up, weight decay, and the mu param, and combine techniques to train small models that achieve similar losses across orders of magnitude of learning rate variation. We explore two cases where instabilities can be predicted before they emerge by examining the scaling behavior of model activation and gradient norms. Okay, so growth of logits in attention layers, that makes sense. Divergence of output logits from the log probabilities, that doesn't, but I'm assuming they'll explain it. High learning rates is where these instabilities occur. And so, and the mitigation that works for large models also works for small models. So I think what so from what I'm understanding so far, they're trying to study these things at a small scale because that's more compute efficient. And they're finding that what applies at small scale also applies at large scale, I think. That's kind of what I'm taking from. Okay, let's look at this chart. because they've put it in the front page. Figure 1, qk-layernorm. So I still got to look that up. If they don't explain it, we will go to this. So let me just copy this. All right, so we'll come back. qk-layernorm enables stable training across 3 orders of magnitude of learning rate variation. Top. For transformers with n parameters, we plot the effect of learning rate on final evaluation loss. So here's learning rate from 10e-4 to 1. And here's the final eval loss. So it goes down, it plateaus, and then I think it's exploding for all of them. This is, what is this, 2 million parameters, and then it goes up to 1 billion. Bottom plot, we use LR sensitivity to summarize the top plot. LR sensitivity measures the expected deviation from optimal when varying learning rate across 3 orders of magnitude. So LR sensitivity, expected deviation from optimal, don't know what that means. qk-layernorm reduces LR sensitivity, but LR sensitivity still increases with model scale. So this slope is positive, so it still increases with model scale. And I think blue is qk-layernorm, and that LR sensitivity drops when you use qk-layernorm. And then the yellow or orange, or I guess tangerine, is without qk-layernorm, and that explodes earlier is what I'm seeing, right? This is like 10e-2 and it's already exploding. Whereas with qk-layernorm, you can increase the learning rate by an order of magnitude or more, and it'll still be stable, and then it'll collapse. So yeah, obviously, I've just kind of interpreted the chart, but I still don't know what qk-layernorm is, and I don't really understand LR sensitivity. Okay, when training large transformers, researchers have reported instabilities which slow or destabilize training. All right, we want to reproduce, study, and predict training instability in transformer models. We find that measuring the relationship between learning rate and loss across scales is a useful tool to identify instability. So I think this is a good general concept, learning rate and loss relationship. LR sensitivity measures the deviation from optimal performance when varying LR across more orders of magnitudes. So going back here, let's try to give this a shot here. So this is 10e-2 at 10 to the 7. Here's 10 to the 7. Well, not really. I guess maybe this one, right? This one or this one. So the plus sign. So yeah, I don't understand what deviation from optimal means still. So let's see. We show that 2 sources of instability at scale can be reproduced in small transformers, so we can study them without large resource. Growth of logits and divergence of output logits. Instabilities appear at high learning rates in small models. So that's what we saw, that explosion. Interventions are effective at large scale and small scale. And this allows training across 3 orders of magnitude. Okay. All right. Then they look at other techniques, and they employ these things. When employing qk-layernorm and z-loss regularization, these other techniques usually have little impact on the range of learning rates at which models can be stably trained, but do affect the sensitivity to learning rate within this range. A longer warm-up reduces learning rate sensitivity, as does the independent scaling of learning rate and weight decay. One interesting finding is that scaling depth increases LR sensitivity at a faster rate than scaling width. Okay, it is possible to predict an instability before it emerges. Our investigation shows that gradient norms decrease with both scale and learning rate, such that the default AdamW epsilon hyperparameter is too large. This causes updates that are too small. We connect this phenomenon and the attention logic growth instability to parameter norm growth. So that I don't really understand, so we'll come back to that. Overall, we believe our work presents new scientific opportunities. Cool. All right, measuring the relationship between learning rate and loss, examining scaling trends for model characteristics. They train small models, similar setup as GPT-2, decoder only, autoregressive loss. So if we look at more infrastructure details, Flax, JAX, and TPUs, training infrastructure. We shard the model in optimizer states as an FSDP, compiling with JIT. Don't know what Orbax is, and grain. Okay, sequences are packed, so no padding is required. Just as an aside, this is something I need to learn more about. Modern BERT has open sourced their sequence packer, so I want to check that out. If a sequence has less tokens than the context length hyperparameter, then an end of sequence token is appended, followed by the beginning of a new sequence. That makes sense. Okay, they use AdamW, gradient clipping. Default warm-up is 5,000 steps. Default number of total steps is, what is that, 10,000? 100,000? Linear schedule for warm-up and cosine decay. Minimum learning rate of 1e-5. Independent weight decay of 1e-4. And auxiliary z-loss with coefficient of 1e-4. Don't know what that is. Let's take a look. Okay, what is z loss? Okay, it's not in there. Z loss, auxiliary loss of z loss, log squared z to encourage the softmax normalizer Okay, let's say auxiliary z loss. We followed recommendations from Palm, which is the paper we just saw, and added the auxiliary z loss. In short, the z loss prevents the logits from drifting too far away from zero, which can cause unacceptable round-off errors in BF16, and encourages the logits to be normalized log probabilities. The auxiliary penalty was found to increase training stability. So z loss is log z squared times a penalty weight. So it sounds like it decreases the loss, makes it closer to zero for rounding reasons. All right, it's probably more to that, but we're gonna keep going. Cool. Okay, we use pre-normalization with qk-layernorm. So I don't know if they're gonna explain qk-layernorm, so we might have to let's just look at this. Okay, parallel layers query key normalization. in scaling VIT beyond prior works, we observed divergent training loss after a few thousand steps. In particular, this instability was observed for models with around 8 billion parameters. It was caused by extremely large values in attention logits, which led to almost one-hot attention weights with near zero entropy. To solve this, we adopt the approach of Gilmer et al., which applies layer norm to the queries and keys before the dot product attention computation. Specifically, the attention weights are computed as layer norm of inputs times weight of the queries. Then they do multiply that by the transpose of the layer norm of the inputs times the weights of the keys. So if I'm understanding this correctly, so D is query key dimension, X is the input, yeah, LN stands for layer normalization, WQ is the query weight, and WK is the key weight. So they're taking a layer norm after applying the matrix multiplication to the individual weights, and then they do the query Q transpose matrix multiplication, and then the scaled softmax. Okay, I think that makes sense. Section 3.1, so they will go into it. We do not use any biases, and the layer norm epsilon remains at the default value. We jointly scale up the embedding size. We do not use weight tying. We use rotary positional embeddings in C4 for training data. D is the model dimension, the embedding size. Hidden dimension is 4D in GELU activations. 1 over square root D scaling, which we saw in that other paper. Normally distributed embedding initialization with a standard deviation of 1 over square root of D. The remainder of weights are initialized with a truncated normal distribution with inverse root fan-in standard deviation. Not sure what that means. Default batch size is 256. Each batch element has a sequence length of 512 tokens. Sequences are packed. We use the vocabulary from this, which has 32,000 and uses a sentence piece tokenizer we train on TPUs. All right, I will bite. What does this mean? Truncated normal distribution with inverse root fan-in standard deviation. Okay, theoretical considerations. Yeah, I had a feeling this is not going to work. All right, I'm going to abort this wormhole, and we're going to keep going. Train on TPUs and bfloat precision, and okay, cool. All right, let's see. I still don't understand this learning rate sensitivity. So, it's useful to plot the relationship between learning rate and loss. Instability is an explosion of the loss at high learning rates. Reveal how the lowest unstable learning rate changes as a function of model size. Okay, here we go. LR sensitivity measures the deviation in final validation loss from optimal when sweeping learning rate across 3 orders of magnitude. If a model fails to train at high learning rates, then LR sensitivity will be high. There are cases where LR versus loss curves and learning rate sensitivity are no longer meaningful. For instance, if an intervention changes the meaning of learning rate. So let theta equal A eta denote the model weights, theta, obtained when training with learning rate, eta. This is eta, right? I'm pretty sure. And let L phi denote the validation loss. Okay, so we're training model weights with a certain learning rate and taking the loss. For a learning rate change, a comma b, let L star denote the loss obtained with the best learning rate. So L star is the minimum value of the loss of the model weights that are trained with a certain learning rate. Moreover, let L0 denote loss at initialization. Then, learning rate sensitivity is defined as the expected value of the minimum of either the given loss at a certain learning within a comma b, or the initial loss minus L star, which is the loss obtained with the best learning rate. All right, let's grab this. And we're going to go to Claude. And we're going to say one of my favorite prompts. Explain LR sensitivity like I'm stupid, but use necessary jargon. LR sensitivity measures how much your model's performance suffers when you don't pick the perfect learning rate. Imagine you're training a neural network and testing different learning rates between values A and B. The formula for LR sensitivity is this. L star is the best possible loss, so that's your optimal learning rate. L naught is your starting loss before training. LA eta is the loss when using learning rate eta. E is the average across all learning rates in your range. Lower LR sensitivity is better. It means your model is forgiving when you don't pick the perfect learning rate. Is more forgiving when you don't. Higher sensitivity means your model's performance drops dramatically with suboptimal learning rates. Okay, I think that makes sense. Can you give me an example? Simple example with real values. All right, so we're training a model with 3 different learning rates. 1 eneg 3, 2, 1, 0. You get these validation losses, 2.5, 2.0, 2.8, 3.5. So the best learning rate is 1 eneg 2, and the loss is 2. Let's say the initial loss before training is 4. So L star is the best loss, so that's fixed. The minimum of the learning rate that you get, or sorry, the loss that you get given a learning rate and the initial loss minus L star. So the minimum of 2.5 minus 2 is 0.5, 2 minus 2 is 0, 2.8 minus 2 is 0.8, 3.5 minus 2 is 1.5. The average is the sum of those divided by 4 is 0.7. So the LR sensitivity is 0.7, meaning on average your loss is 0.7 higher than optimal when using a random learning rate from your range. All right, I think that makes sense. So the optimal is, well, let's just ask. So the optimal learning rate is not something theoretically derived, but a empirical result yes, it's empirically determined, not theoretically derived. It's simply the learning rate that produces the lowest loss. Okay. LR sensitivity measures how much your worst results get if you don't hit that sweet spot. That's really cool, right? Because if these losses were a lot more similar to each other, it's like it's okay if you don't get the right learning rate. It's like more forgiving. So now this makes sense. All right. Cool. That was one of the main things that I didn't understand. So let's roll. Okay, unless otherwise mentioned, we use 3 eneg 4 to 3 eneg 1 with AdamW. LR refers to the maximum value in a cosine decay schedule with warm-up. We consider learning rates in this set when computing the minimum and the expectation. Great. So the other thing I need to understand, so we got qk-layernorm. Z loss makes sense. It's like basically you're squaring your log loss and multiplying it by a fraction to make it smaller so it stays closer to 0. And then I think the divergence of output logits was the last main thing that I don't understand. So to study instability, we also find it useful to examine scaling trends for model characteristics such as gradient or activation norms. Good. This method is helpful for predicting instabilities in contrast with previous work on scaling, which primarily focuses on trends relating model scale and loss. Okay. Yeah, so we're just kind of this idea of predicting before they emerge. Predicts when the logic growth instability may cause divergence. All right, so let's go. Growth of logits in attention layers and divergence of the output logits from the log probabilities. Still don't understand that. By examining LR versus loss curves, we show that these instabilities can be reproduced in small models by using high learning rates and that the mitigations employed at scale are effective in this regime. All right, attention logic growth. Here we go. Researchers have previously documented that transformer training fails when the attention logits become large. This issue emerged when training a VIT model with 22 billion parameters. In the self-attention layer of a transformer, queries Q and keys K are combined to compute the attention logits. Z equals qk. What is this? Is that matrix multiplication? Explain Zij to me. Dot product. Oh, right. Okay, yeah. So I guess, yes, matrix multiplication, but the main thing is dot product. Dot product divided by scale root of the dimension. Okay, the attention logits are passed through a softmax to produce attention weights, which are used to combine values V. Degani observed that the attention logits Z become large, which they referred to as attention logic growth. As a result, the attention weights collapse to one-hot vectors, which was named attention entropy collapse. So I think when you take a softmax of a large value, it collapses to 1, right? And very small values go to 0. To resolve this issue, they propose qk-layernorm, which applies layer norm to the queries and keys before computing the attention logits. All right, so let's continue this and say, are the one-hot vectors a result of softmax of large values going to 1 and softmax of small values going to 0? Yes, when they become extremely large, softmax operation produces a probability distribution that approaches a one-hot vector. When one value, zk, is much larger than all others, e to the zk dominates the sum, causing softmax of zk to be 1 and softmax of z, not k, to be 0. This attention entropy collapse means each position primarily attends to just one other position, instead of distributing attention across multiple relevant positions, limiting the model's ability to aggregate information effectively. Cool. We find that models need not be large to exhibit instability related to attention logic growth. That's cool because I can test that, right? Because I'm doing stuff with small models. The maximum learning rate at which small models can be trained increases when using qk-norm. So figure 1. So yeah, we can small model. So here's 1,000,000 parameters. If we use qk-norm, the blue collapses like 1 or 2 orders of magnitudes later. Great. without qk-layer norm, the learning rate at which models diverge becomes smaller with increasing model size. Smaller with increasing model size. So diamond is the largest. Yeah, so there's the tangerine lines collapse as you go higher and higher weights. So the plus sign is 9 million. That's like, what is that? Like 5e neg 2. The diamond is 1 billion. That's 1e neg 2. Okay. By contrast, models with qk-layer norm exhibit considerably lower LR sensitivity and train to low loss at high learning rates. As a result, or as a highlight, qk-layer norm allows training a model with 1.2 billion parameters at learning rate 0.3. Both with and without qk-layernorm, norm, LR sensitivity increases at scale. So if we go back up here, LR sensitivity, lower is better, goes up with scale, but is lower with qk-layernorm. norm. And here's 0.123, and here's the 1 billion model, 1 billion parameter model, learning rate is 0.3. That's crazy. I didn't know that was a thing. All right, figure 2 displays the loss and max attention logit for two model scales that differ by 3 orders of magnitude. In both cases, the loss diverges without qk-layernorm. norm. So here's figure 2. The attention logit growth instability appears in small models at high learning rates. So step, loss, step, max attention logit, step, max attention logit, step, loss. Okay, so 9 million, 4 billion, right? The mitigation of applying qk-layernorm norm proposed by Degani is equally effective in small models as large. So that's cool. Maximum attention logit is reported for layer 0, which we typically observe to have the largest. So if I'm going to test this on my own, I should check layer 0. So orange is no qk-layernorm. norm. Blue is qk-layernorm norm equals true. Without qk-layernorm, norm, loss explodes and logit explodes. And with qk-layernorm, norm, it doesn't. But interesting that the loss here is not as bad for smaller models, but eventually it explodes. And LR is 0.1 and LR is 0.01. So very cool that you can still train with a relatively large learning rate. All right, I think this is making sense. Attention logit growth is due to growth in the queries and keys, not due to an increase in their alignment. Instead, we hypothesize this instability could result from the quadratic dependence of attention logits on parameter norms. So if we look at E1, mean query norm, so the query norm increases, query key cosine similarity stays the same, average max attention probability occurs when the norm of the queries and key increase, not due to an increase in their cosine similarity. Okay. All right, here we go. Output logit divergence. Another instability reported by researchers is the divergence in the output logits from the log probabilities. Just as before, we reproduce this instability with small models at large learning rates. I'm going to take a sip of water. All right, let Y denote the model's output logits, which are used to compute class probabilities via softmax. So probability is e to the y divided by z, where z is the sum. This instability occurs when the logits, so y, diverge and become very negative. In contrast to the attention logic growth instability, this divergence occurs towards the end of training. The mitigation proposed by Chaudhry is to encourage log z to remain close to 0. They add an auxiliary loss log z squared, referred to as z loss, with coefficient 1 e neg 4. I still don't understand what divergence means here. Like, is it like when I think of divergence, I think one thing is going in a different direction than the other. So if y becomes very negative, e to the negative number, I think, would become very small, right? So y becomes very negative, and then p would become very close to 0. I think that's what it means, but we'll check in a second. An example of the output logit divergence instability. So output logit mean, weight decay, no weight decay. Output logit goes down to negative 100. Weight decay, it gets delayed. I don't know what this way. I don't know what these lines are. Where are the gray lines? Yeah, I'm not sure. I'm assuming. Okay, sorry, I'm misunderstanding this. So, solid line means z loss coefficient. Dashed line means no z loss. Blue color means weight decay. Magenta means no weight decay. So no z loss, no z loss. These both are z loss. No z loss, no z loss. These both are z loss. We're going to ask Claude. Am I understanding correctly that the divergence taking place is between the logits becoming very, very negative and the probabilities becoming closer and closer to 0? Yes. Output logits become extremely negative. Probabilities approach 0. The paper describes this as a divergence between output logits and log probabilities. As shown in figure 4, the mean output logit drops dramatically, becomes very negative, toward the end of training for models without weight decay or z-loss regularization. The mitigation proposed is to add an auxiliary z-loss term, log squared z, that encourages log z to remain close to 0, preventing this divergence. Very cool. All right, we find that instabilities related to output logit divergence occurs in models with no weight decay regardless of scale, and z-loss resolves this instability. Weight decay also mitigates the instability for the larger models we test. So did we look at figure 3? No, we didn't. The effective output in logit divergence and z-loss mitigation. Models in this experiment have qk-layernorm. So solid is with z-loss, dashed is without z-loss, and in all cases, the dash explodes earlier at lower learning rates. So z-loss allows higher learning rates, and z-loss makes LR sensitivity lower, but so does weight decay, even for no z-loss. So that's interesting. All right, measuring the effect of other non-interventions. Okay. Warm-up, weight decay, and mu param. A longer warm-up reduces LR sensitivity. Figure 5. The effective warm-up length for different model sizes. So, oh gosh, this is a bit. All right, so larger warm-up decreases LR sensitivity, so that's good. So warm up of 50 is up here, warm up of 25,000 is down here. It's hard to tell what's going on here, but it seems like for some of the cases, especially for larger models, warm up impacts more. You get this like delta between the learning rates of when it explodes. Whereas for the smaller models, they kind of seem to explode at the same time, especially for the larger models we test, yeah. Okay, this is most clear for the larger models. Yep, parameterizing weight decay independently of learning rate reduces LR sensitivity. So independent weight decay blue, lower sensitivity, especially for larger models, very significantly, right? This is like 2+ orders of magnitude. The loss explodes, whereas it is stable with independent weight decay. Okay, while this was recommended by Loshkilov and Hutter, it is not common practice in the default AdamW implementations of PyTorch or Optax. We explain the differences below. For parameters theta, let delta equal v over square root of u plus epsilon denote the AdamW update without learning rate or weight decay. For weight decay coefficient gamma, that's gamma, right? Wait, is that gamma? I forget. Lambda. Yes. Okay, lambda. Max learning rate eta and schedule ST in 01. They recommend the update theta minus learning rate times delta minus lambda times, what is that? The parameter, which we refer to as independent decay. On the other hand, the default implementation in PyTorch applies the update. Now, eta scales both terms. So the weight decay is being multiplied by the learning rate. Instead of here, the weight decay is only multiplied by the weight, not the learning rate. When reporting LR sensitivity without independent weight decay, in figure 6, we report minimum LR sensitivity over ranges of this and this because the former is sometimes better centered on the minimum. The default setting is to use weight decay or independent decay. When using independent decay, we set lambda to 1e-4, and without independent decay, we set lambda equals 0.1, and they did a sweep. And seems like yeah, I guess here lower weight decay is better, right? Yeah, that's not as clear to me. Okay, we have so far consistently observed that increasing the number of parameters increases LR sensitivity. We now examine which part of scaling is most responsible. Our results indicate that scaling depth increases LR sensitivity at a faster rate than scaling width. However, at the largest scale we test, independently scaling depth produces a model with lower validation loss. The standard practice of joint scaling performs best at the largest scale and also has a more reliable scaling prediction when extrapolating. So figure 7, scaling width and scaling depth. So depth is increasing layers, and that increases learning rate sensitivity more than scaling width, which is the hidden dimension, which scales it less. All right. Attention logit growth instability occurs more frequently at scale, regardless of whether width or depth are scaled. That's without qk-layernorm. So without qk-layernorm, learning rate sensitivity, no, that's not that one. Jointly scaling leads to lower loss than independently scaling at the largest scale. It also leads to a more reliable scaling prediction. Am I looking at the right one? E2, effective scaling width versus scaling depth. Oh, I see. So here it doesn't get you to the higher learning rate, I think is the more frequently at scale. Yeah, I'm not super clear on that. Can you clarify what this means? Focus on appendix E2, right? E2. The attention logic growth instability occurs frequently at larger scales. What does frequently mean? As the models are increased in scale, the attention logic growth instability occurred at lower learning rates. Okay. Yes. Okay. So it is what I was saying, that we don't get, we don't get as up into the 10e-1 range. All right. Cool. Let's keep rolling. I would like to keep this under 90 minutes, but we'll see. Yang and Hu introduced the mu-param method for parameterizing a neural network. As a product, the optimal LR remains consistent when scaling model width. This section tests the effect of mu-param on LR sensitivity and examines whether mu-param alleviates the need for qk-layernorm. Do they explain what mu-param is? No. Looks like we're going to have to look it up. Okay. Can I search that? So this is the paper, but it's not easy to find it. The maximum update parameterization is given by this. Don't really understand this. Its adoption has been limited due to the complexity of the underlying math. So, stable optimum HPs. I don't know what HPs are. All right, this one I think is going to be out of scope. So mu param does succeed in stabilizing the optimal LR. So mu param actually makes the learning rate worse, but it does make it go a little farther. Yeah, I'm not going to go into too much detail here because I don't really understand what mu param is. It does not improve loss or does not reduce LR sensitivity. Mu param does not alleviate the need for this intervention at higher learning rates. I think this intervention meaning qk-layernorm. Okay. I'm going to skip to the next section. This section recreates the previous plots with additional interventions or hyperparameter changes. Corresponding figures are displayed in the appendix. Changing the number of training steps from 100,000 to, 50,000 or 200,000 does not meaningfully change LR sensitivity. We try applying qk-layernorm across the whole model dimension instead of individually per head with shared parameters. The latter performs better. We use per head qk-layernorm as a default. Increasing batch size does not meaningfully change LR sensitivity. We decrease the number of training steps so that the amount of data is constant. Changing weight decay from 1e-4, increasing decay appears to slightly shift the optimal learning rate right. Logic growth instability is not due to the softmax, as it still occurs with a point-wise variation of attention. Logic growth instability occurs even without softmax. For the point-wise variant of attention here, we replace softmax with a squared value as described here. We add a scaling factor so they try a different, I guess, non-linearity, and it doesn't change the effect. Okay, so that laid out the two instabilities and how they mitigate it. And qk-layernorm and z-loss was how they mitigate it, and then weight decay also helps. That's kind of my main takeaways. Now it's about predicting attention logic growth instability from scaling behavior of model characteristics. A central question when studying instabilities is whether they can be predicted. We track the attention logic maximums across model scales and fit a curve to the data. We use this to predict that a 4.8 billion parameter model will be unstable at learning rate 1e-2 without qk-layernorm, and run an experiment to confirm this prediction. Figure 9 plots number of parameters versus max attention logit at different learning rate values. So that's figure 9. Max attention logit, number of parameters, qk-layernorm, and I think this is their target that they were correct for. Additional experiment to validate predicted instability. Yeah, so their experiment was on the line. Okay. We first noticed that all points with attention logits above 1e4 diverged. All points with attention logits above 1e4. So 1e4. So first notice, what is, okay, let's see. When the maximum value of attention logits exceeded 1e4, the model's training would consistently become unstable and diverge, meaning the loss would explode and training would fail. So, oh, I see. So instability. So above 1e4, we have these x's, which is loss exploding. So that makes sense. The quadratic fit predicted that for LR1e-2, the next model scale would cross that value. This model diverged as predicted. Our fit closely extrapolates to predict the value of the max attention logit. Cool. One question unresolved is whether we could have predicted that instability arises when the max logit exceeded 1e4 without manipulating learning rate and model size. We take initial steps towards an answer by transplanting different values of max attention logit into a small network with 10 million parameters. For different constants, I don't know what this letter is. Let's do this. Can you explain this paragraph? And what is that k working symbol called? Is that psi, maybe? I don't know. Represents a constant value they use. They designed a method to artificially set the maximum attention logit to different values in a small network to test whether the 1e4 threshold holds independently. They created a transformation function that scales query and key values to achieve specific attention logit maximums. They tested different kappa values to force different maximum values. They found model performance degraded around 1,000. By 10,000, the model performed worse than a simple zero-layer bigram baseline model that lacks attention mechanisms. This experiment confirmed that high attention logit values directly harm model performance, supporting their earlier observation about instability regardless of how those values occur. Regardless of model size. Yeah, I'm not really clear on that. Let's try one more time. I'm not very clear on this. Can you explain it? Like I'm stupid. That usually tends to work. Does having attention logit values above 10,000 always break the model, no matter what causes those high values? They took a small model, they artificially forced the logits to specific values. They measured how well the model worked with different forced values. When they forced logits to around 1,000, the model started performing worse. When they forced attention logits to 10,000, the model became so bad it performed worse than a super simple model with no attention mechanism at all. This confirmed their theory that attention logits above 10,000 directly caused the model to break down. It wasn't just a coincidence. Okay, so they are saying it wasn't just a result of a particular learning rate or model size they chose. Yeah, certain. Okay, I see. Okay. All right, I think that makes sense. Searching for new instabilities via scaling trends of model characteristics. This section examines whether the scaling behavior can be used to predict new issues. We examine scaling trends for the gradient, root, mean, square. RMS of gradient is the gradient squared average, square root. This figure reports the RMS for the first layer of the MLP, though we observe similar trends for other layers. As models get larger, the value that grad RMS approaches is cause for concern. Figure 11. So models get larger. What does that mean? So that means this. Gradient RMS does not decrease. It gets more negative. And we have the number of parameters going from millions to billions. Okay. All right. Okay. The value that grad approaches concern at the largest scale. An obvious mitigation for this issue is to simply lower the AdamW hyperparameter from its default of 1e-8. We conduct this experiment for a 4.8 billion parameter model. Decreasing epsilon, the hyperparameter, improves loss and mitigates the collapse in grad RMS. So blue avoids the collapse of the gradient norm, and it also decreases the loss. We believe this improvement will only increase at scale. On the other hand, increasing epsilon to 1e-6 results in an instability. So here's the instability, I think, where the grad RMS explodes by a couple orders and the loss explodes. That's for sure an instability. Grad, illustrating the grad and update RMS throughout the training at the largest scale and learning rate we test. When the grad RMS reaches epsilon, the update RMS becomes small. The top row displays the root mean square of the gradient for the first MLP layer at different blocks throughout the network. When the grad RMS drops below the AdamW epsilon hyperparameter, the magnitude of the update decreases. Okay, so 1e-6 diverges. 1e-8 is default. 1e-15 is, I think, better because the root mean square stays between 0 and 0.1, which is, I think, what we, or no, wait, between 0.1 and 1? I'm not sure. All right, let's ask. This chart shows what happens when the gradient root mean square values approach or fall below the AdamW optimizer epsilon. This figure contains 8 graphs in 2 rows. Top row shows gradient RMS values for the first MLP layer across 4 different blocks. Unscaled update RMS values for the same blocks. 3 different epsilon values are tested. Magenta line is 1e-6, cause model to diverge. 1e-8 is default. 1e-15 is smaller epsilon. When gradient RMS drops below the epsilon value, blocks 16 and 22, gradient RMS drops below the epsilon value. So 1e-6, and here it drops below. 1e-8 drops below. 1e-15, it does not drop below. But here, 1e-6 drops below. 1e-8 drops below. 1e-15 does not drop below. The magnitude of parameter updates decreases significantly. Unscaled update. Oh, I see. So this is, I think this is the top row. The magnitude of the update decreases. So I think this is the gradient update. So using smaller epsilon maintains larger update magnitudes even when gradients become small. What is a update magnitude and how is it different from a gradient? Partial derivative. Oh, I see. So it's the, right, it's the actual change applied in standard gradient descent is with the gradient multiplied by the, I see, the learning rate. Okay. So even though the gradient decreases, the update magnitude, what was it again? Even when gradients become small, it maintains large update magnitude. So the gradient becomes small here, but it maintains a large update magnitude. Which leads me to the question, How can a gradient be small, but the update magnitude be large? Oh, I see. In adaptive optimizers, several mechanisms can cause updates to be larger than the raw gradient magnitude would suggest. Normalized by second moments, the epsilon parameter, momentum. When epsilon is reduced, updates remain significant even when the gradients become very small, preventing the training stagnation shown in blocks 16 and 22 with the default epsilon. So the stagnation, I think, is these ones here. And this one here. Stagnation meaning that the update is very small. 100 times smaller. Okay. I'm not as familiar with the AdamW optimizer, so there's a fast AI course lesson that I haven't gotten to yet, so probably make more sense once I get there. Okay. Yeah, I think that's fine for that. Okay, related work mainly focuses on the effect of known interventions. The related work has primarily been discussed when relevant. We talked about attention growth instability, logit divergence, fast loss spikes, quick increase in the loss that often eventually recovers. I've actually been seeing that recently in some training runs for small LM 135 million. The edge of stability and fast spikes. The conventional understanding of gradient descent predicts that loss in stability only occurs when the learning rate exceeds 2 divided by lambda max h, where h is the Hessian. When training neural networks with large batch SGD, the loss curvature constantly evolves. Alright, I'm going to skip over this part. Adaptive EOS can also result in periodic loss spikes when progressive sharpening pushes the preconditioned sharpness above the stability threshold. Not sure about that either. Okay, what do we have here? While our work investigated mu-param, there are additional parameterizations for which it would be interesting to explore. Okay. As the compute required to train the largest models continue to increase, it becomes increasingly important to understand if training will be stable. This paper has shown that useful insights on stability can be found when studying small transformers. We hope that this opens new opportunities for impactful research, which benefits large runs without access to large resource pools. So I think my main takeaway going back here is that Z-loss improves stability, qk-layernorm improves stability, and it also improves the, I guess you don't need to do as much of a hyperparameter sweep because there's a lower deviation from optimal learning rate on average. And then I think the other takeaway would be here, which is that you can fit a curve to small models. I mean, this goes up to, what is that, 10 billion or 1 billion? So it's not super small, but you can kind of predict larger model instability values, such as max attention logit, for a given learning rate if you train small models. So I imagine if you had compute for small models before you did your actual training run, you could kind of predict stability or instability, and then that's how you would pick your learning rate. So that's kind of another takeaway I have. And I know there's a lot we didn't cover. We did look at many of the appendix. I don't think we saw this one. For various learning rates and model sizes, we display the gradient root mean square and the unscaled update root mean square. The unscaled update is the update returned by the optimizer before scaling by learning rate. I see. So the Claude was talking about the update being multiplied by the learning rate, I think. The gradient and update are shown here for the first MLP layer. The update RMS falls when the grad RMS approaches the epsilon of 1e neg 8. So here's the update collapsing. Here's one e, what is this? No. The unscaled, the update RMS falls when the grad RMS approaches the epsilon of 1e neg 8. So grad RMS, when it approaches 1e neg 8, so it's going down. So, okay, so here's different learning rates. The update falls. So this seems to be a relationship between learning rate and unscaled update, I think. Let's just see. Let's ask. No. Figure E13 illustrates the relationship between three key metrics across different learning rates and model sizes. So here's model size. Oh, I see. The colors are the model sizes. Okay. Loss, gradient RMS, unscaled update RMS. The figure shows how these metrics evolve during training steps for different model sizes and learning rates. The key finding is that when gradient RMS approaches the AdamW epsilon value of 1e neg 8, the unscaled update RMS decreases, particularly visible at higher learning rates for large amounts. Oh, I see. So this dip. I think it's saying this dip. I'm not 100% sure. Because when this falls here, that dip is kind of there. Yeah, I'm not super clear. Where gradients become too small relative to the optimizer's epsilon parameter, causing ineffective parameter updates during training. So if we look at a large model, this one, gradient is at 10e neg 5. It drops to 10e neg 6. If we go down here, yeah, I don't know. I'm not super clear on this relationship, to be honest. It was a lot more clear, relatively speaking, when we looked at this, right? Here, I could see that grad RMS drops here, and the update collapses. Whereas for 1e neg 15, even when the grad RMS drops, the update doesn't collapse. And I might have missed this, but let's ask one more question. Do they explain why an epsilon value of 1e negative 15, even though causes a drop in gradient RMS, doesn't cause a drop in unscaled update RMS? The paper doesn't explicitly explain this. However, based on how AdamW works, I provide a technical explanation. The denominator becomes denominated by epsilon rather than the actual second moment. This artificially reduces the update magnitude. So it sounds like if you're dividing by epsilon and second moment, approximately the gradient squared. Yeah, I'm not going to dig into that because I don't fully understand AdamW yet. Okay, yeah, very cool paper. I guess the questions that come to my mind is like, is qk-layernorm a thing? Is z-loss a thing? I don't know. I certainly haven't seen them like explicitly being mentioned in like training frameworks. Maybe they are and I'm just not looking for it. Second thing that comes to mind is I absolutely want to measure, these attention logit mean values, these output logit values, and, kind of, I'm not sure how easy or difficult it would be to implement qk-layernorm or zloss, but that would be really cool to like try to implement that and train a small model, like a tiny stories type model. So yeah, this is like, honestly, this is one of the most exciting, kind of interesting, approachable papers and concepts that I've come across. Anything related to small models I'm interested in because that's where my access is. That's I have access to Colab, or I have access to Paperspace or Jarvis AI Labs. So anything in the small GPU range, small model range is where I want to focus. And I don't always come across as much because I guess I'm not looking for it. So I'll definitely check out Worstman et al. Papers and hopefully do some more of these videos around that. So thanks for watching, and I'll see you next time.